Okay, so I want to talk about Gull's theorem, but what Gull's theorem was is just actually a proof of Bell's theorem, and I think I need to start by explaining to you Bell's theorem. And I already started writing it down here, and I will read through what's written here and explain the important stuff. So, Bell's theorem says there do not exist a probability space with, defined on it, a collection of random variables, taking values in -1 and +1, having a certain probability distribution. That probability distribution is called the Singlet Correlations, and it's given in this table, or well, this is a description of the joint distribution of one of the A's and one of the B's. There are random variables A subscript theta and B subscript phi. They take values +or -1, and they have in pairs a certain joint probability distribution. The expectation of A theta is 0 for all theta. The expectation of B phi is 0 for all theta, all phi. And the expectation of the product of one of the A's and one of the B's, A theta B phi, is minus the cosine of the difference between theta and phi. Let's call that R. Now, knowing that those random variables take the values +or -1, and knowing that their mean values are 0, we know what their marginal distributions are. They're all Hadamard variables, +or -1 with equal probabilities a half. The expectation of the product is R. This tells us what the probability of, this is enough information to fill in the rest of the probabilities, what the joint probabilities must be. And I've done this already in this little table. The probability they're both equal to -1 is 1/4 of 1 plus R. That's also the probability that they're both equal to +1. The probability of -1 + 1 and of +1 - 1 are both 1/4 of 1 minus R. And we get this little table of 4 probabilities adding up to 1. Marginal distributions are half-half, half-half, and R, the expectation of the product. The physicists call that the correlation, meaning the uncentered, unnormalized product moment, so just the expectation of the product. But it's also the statistician's Pearson correlation as well, since the standard deviations of A theta and B phi are 1, and the means of A theta and B phi are 0. So here's the probability distribution which we want, the joint probability distribution of any A and of any B. And Bell says that this is impossible to have. And he shows that it's impossible to have by showing that it already goes wrong if you only would want to have 2 particular thetas and 2 particular phis. And these are his choices, 0 and 90 degrees, and 45 degrees, and 135 degrees. Now, what's special about them? Well, actually, they are also the solution of a minimax problem. They're the kind of the worst thing that quantum mechanics can do against the best that classical physics can do. But let's not go into that just now. The angles are 0 and 90 degrees for Alice. They're 45 degrees and 135 degrees for Bob. I have to explain to you what Alice and Bob are doing here in a moment. But okay, we get used to that. The differences between those angles are plus or minus 45 degrees, and one of them is minus 135 degrees. So the cosines are all plus or minus 0.7, and one of them is plus 0.7, and 3 of them are minus 0.7, and I've written them out there, and you better check that. And what is the consequences of those particular choices is that the correlation between A theta 1 and B phi 2, R1 2, is plus 1 over square root of 2. The other 3 correlations are minus 1 over square root of 2. And so 1 minus the sum of the other 3 does equal 4 times 1 over square root of 2, 4 over root 2, that's 2 root 2, that's about 2.8. Now, Bell proves that this is impossible, and here's the proof, and it's an extraordinarily simple proof. Let A1, A2, B1 and B2 be 4 random variables, taking the values -1 and +1, and consider the expression A1, B2 minus A1, B1 minus A2, B1 minus A2, B2. You can write that as A1 times B2 minus B1, and then you've got left minus A2 times B2 plus B1. And those two terms in brackets, one of them is going to be 0 and the other is going to be plus or minus 2, because either B1 equals B2 or B1 equals minus B2. So one of those terms is 0, the other is plus or minus 2. Well, they get multiplied by A1 and A2, which are plus or minus 1. So that whole expression is equal to plus or minus 2. Consequently, its expectation lies between -2 and +2. And its expectation separates into one expectation minus 3 others. And so one correlation minus the sum of the other 3 must lie between -2 and +2. Now, where does this idea come from? That, well, there are two ideas to be explained here. One is the quantum mechanics ideas, which lead to a setup, an experimental setup, where you would expect to see these correlations and these expectations. And the other part is classical physical reasoning, why you would expect the existence of those random variables, A1, A2, B1, B2. Now, for the classical physics part, let's have a look at this picture here. Consider an experiment in which there's a source which emits 2 particles which travel some way or other to 2 distant locations where there are devices, there are labs. One is owned by Alice and the other one is owned by Bob. And in those labs are big pieces of experimental apparatus called A and B. And what those do is they receive a particle coming from S, and then the machine, well, they don't only receive a particle coming from S, they have to be preset by Alice choosing an angle alpha and Bob choosing an angle beta. Sorry, these were theta and phi. Now I'm going to call them alpha and beta. Same difference. So Alice and Bob each insert an angle into those boxes, and they are at opposite ends of that big long box, and they go into those machines called A and B. And then something happens, there's some whirring sound and clinks and clunks, and then 2 pieces of paper get printed and ejected at each end, and on them are written plus or minus 1, and we call those X and Y. X and Y are outcomes of measuring the particles which have arrived at A and B, and they're being measured in ways which are influenced or determined by Alice and Bob's choices, alpha and beta. In fact, in Bell's proof, it's not even an angle which is introduced, it's just a switch, a toggle switch, which is initially in an off position and then is flipped to position 1 or 2. And similarly, on Bob's apparatus, there's the toggle switch, which is initially in a neutral position, and Bob clicks it, triggers it to position 1 or 2, and inside the machine that corresponds to choices of angles. I mean, machines may start rotating through those angles, but other things could happen. It doesn't matter. Now, suppose there would be a classical physical description of this experiment. In first instance, it could be a very classical physical description. It would be completely deterministic. And so what determines those outcomes X and Y? Well, it must be function of the initial state of the big system inside the big box, which I'm going to call little omega. Of course, I'm only interested in the parts of that which are relevant. So a little omega doesn't describe every particle of matter and space throughout the whole big box, but just what's relevant. But it doesn't matter. Little omega describes what's important, which is going to predetermine what comes out of those boxes, together with the outcomes, together with the settings, alpha and beta, chosen by Alice and Bob. So there must be functions in a deterministic physics world, which are called A and B, which depend on alpha and beta and omega, and which take the values plus or minus 1, and those are what we call x and y. Now, when we do this experiment in the lab, we arrange and we take good care that that little x gets ejected out of the machine, printed on a piece of paper, with plus or minus 1 printed on it, so fast after Alice has inserted alpha into the machine, that there's no way that Bob's choice, beta, could have influenced it. So actually, A doesn't depend on beta, it only depends on alpha and omega. And B doesn't depend on alpha, it only depends on beta and omega. So there are some functions, A of alpha and omega, and B of beta and omega, and they generate x and y. Now we think of this experiment being repeated many times, and each time little omega is, so imagine that everything sort of being cleaned and reset and restarted, then the initial state little omega is different, or can be different every time, and we'll think about it as being drawn from a probability distribution again and again. A probability distribution P on some probability space omega. So we get random variables, A alpha and B beta, or A theta and B phi, and that's the reason for Bell's assumption, which we showed does not allow this experiment to create the singlet correlations. Now, you may feel that this is too rigid and too deterministic, and maybe truly random things go on in A and B, which need to be modeled by adding extra randomness into the model. Well, and there's no problem in doing that. We just add to little omega mathematical variables, omega A and omega B, with some joint probability distribution, and little omega A and omega B now mathematically determines the outcomes x and y. Omega A and omega B aren't aren't physically real. They're not there in advance, but they are just used in the mathematical model, which this is. It is a mathematical model. It's a mathematical model which is supposed to model the actual experiment. So in particular, it's supposed to reproduce the randomness, the probability distributions, which we expect to see in the actual experiment done in the quantum physics lab. Okay, so I think that's what I'm going to tell now for the time being. So now I'm going to stop this recording.